computer. Okay, so we've got some new stuff to go over. So your exams are all in, and that they're graded. So that's part of your grade now. So that is one of the parts of the grade that doesn't drop. It doesn't change. So right now it is the biggest part of your grade. Also, we've got new homework this week. It is due Sunday. New extra credit this week. It is due Friday. New quiz this week. It'll become open on Thursday, close on Friday. And that's pretty much it. No other real big news class announcements. Everything I have for the grade so far is already posted. So you've got everything that you probably should have contributing to your grade so far. That said, a couple people did point out some issues with the automatic grading coming over from Pearson. I was able to correct those, so thank you for bringing those to my attention. That's usually how I know that there's a problem, so don't be afraid to bring those up. And that's pretty much it. So I'm going to go ahead and get started on PowerPoint. So I've got a few problems that I've worked into here. I've also posted the slides that I'm presenting now. They're currently in the week 4 content under class materials. So you can go there and take a look at those things if you want to have them handy while we're going through this. So they were posted. And hopefully you had a chance to look at the pre-questions that I posted, so you could see, the kinds of things that are fairly representative for a unit that contains these things. All right then, I'm going to go into a sharing screen mode. And this, minimize this, so today's class, the 9th, and working on, we've got solution concentration, molarity, dilution. We're going to look at different kinds of solutions that contain electrolytes and non-electrolytes and solution stoichiometry. And that's where we'll end for today. Next week, or not next week, but on Thursday, what we'll pick up on are the kinds of reactions that can happen in solution. So you can take a look and see, look ahead a little bit. And part of the electrolyte, non-electrolyte stuff would be sort of a prelude to that. And that'll take us through the end of that chapter, 5th chapter, I believe, intro. And then we've got our important dates, which I had already previously mentioned. Our quiz opens Thursday due Friday. Extra credit due midnight on Friday. Homework due midnight. So we've got those different things that are coming up. So let's talk about solutions. So solutions are something we have already talked about a little bit in general chemistry, where we mentioned at the very beginning that it's a homogeneous mixture. And it's a specific kind of homogeneous mixture. For us, it tends to be liquid, although many of you could consider air to be a gaseous solution. It's a homogeneous mixture. And there are 2 parts to this that we want to pay attention to. One is the solute, which is whatever we have in lesser amount. The other is the solvent, which is what we typically have in greater amount. And you can think about the solvent as this is the thing the solution is made of. And you can think of the solute as this is what we put into water to make the solution. That's what a lot of people tend to think of these things. An example of that would be Gatorade. Gatorade is a solution. It's a homogeneous mixture, so is my Diet Coke. So the solvent in both the Diet Coke and Gatorade is water. Okay, so that is more water than it is anything else. A bunch of stuff is added to that water. In the case of Gatorade, salt, sugar, flavoring, trade secrets, whatever it is they put in to make that drink what it is, those are the things that are put there. However, if you were to take like a molecular survey, more molecules would be water than anything else. So it makes it a solvent. And so we can talk about how much of this solute is put in compared to the solvent, and that gives us to a unit of concentration. This chapter deals with 1 unit of concentration, which is molarity, and we'll get into what that is. I think you've already seen it if you've taken basic, but we'll get into what that is in a little minute. So the basic idea behind a concentrated solution is that it's a solution that has a lot of stuff in it. Or if we're talking about just one kind of thing, a whole lot of that thing. A lot of salt, a lot of sugar, a lot of whatever. The diluted solution is one that does not contain anywhere near as much. So the amount of this stuff here is way less. So if we talk about a concentrated solution, it means there's a lot of stuff in there, dilute solution, not a lot of stuff in there. But the ratio of stuff to the amount of solution that you have, that is its concentration. And the one unit we're going to be working with is molarity. When you start second semester of 2046, there are a lot of other units that end up being put into this. So you'll want to take a look at those. Now, I'm going to point out a couple of things here. One is the unit of concentration we're working with, which is molarity. Two is this graphic over here. So what you're seeing here is a piece of glassware. I've got one here. I've got a bunch of these in my garage. That's why. But I've got a 500 milliliter volumetric. Now this is special. This is different from a beaker. Beaker is a very different piece of glassware. This is a good piece of glassware for holding stuff, not for measuring stuff. Even though there are these gradations here on the side, the volume on this is plus or minus 5%. Okay, so it's not a good piece of glassware for measuring. This has no gradations on the side, but it has one line right here. At this line, this will contain 500 milliliters of solution. So this is called volumetric. It only contains one volume with any level of precision, 500 milliliters. Above that line, no idea how much. Below that line, no idea. At that line, 500 mils. So this gives me like 2 places past the decimal. As a special piece of glassware, if anything were to change about its shape, its volume would change. So this that they're doing right here is a no-no. If I ever see you in a lab adding solid directly to a volumetric flask, that's the end of our relationship. Putting solids into a volumetric flask can scratch the inside of the flask, increasing its volume, making it no longer volumetric, just fundamentally shaped. So we always make our solutions outside of volumetric flasks and then pour it into them very carefully. If we were in class, I would do like an actual demonstration of this. For here, the graphic will have to do it. Now, we add water up to this liter mark. Now, this is someone who with Herculean strength who's going to squeeze an entire liter of liquid out of this squeeze bottle. Again, there are much more efficient ways, but I think you get the idea. And when you're at this line, we have a solution that contains 1 liter. So if I have 1 mole of sodium chloride, which weighs 58.44 grams, and I put it into a solution that has a final volume of 1 liter, then I can say I've got a 1 molar solution of sodium chloride. Every liter of this solution will contain 1 mole of sodium chloride. No matter what volume of solution I took out of this, its concentration would be 1 molar. And that is moles of solute per liters of solution. Okay? And there are ways that we can calculate this. Now, this is actually, if you're going to go into work in the lab of any kind, this is one of the things you really do need to know how to do, which is to prepare a solution with a known concentration. Usually, someone will ask you to make a solution. They'll tell you what its concentration should be and how much you should make. And those are the only 2 things you need to know. So the question here becomes, how would you prepare 250 milliliters of a 0.015 molar solution of potassium sulfate? Okay. The solution involves doing 2 things. 1, finding the moles of the solute, and then dividing that by the volume of the solution. So a 0.015 molar solution of potassium sulfate would contain 0.015 moles for every 1 liter that's made. I'm going to make 2 milliliters. So 0.015 molar per liter times that number of liters is going to give me 0.00375 moles of potassium. Well, this says sulfate. This says nitrate, it should be sulfate. I don't know why I don't change in a minute. So that's how much we end up making there for how many moles of this stuff that we need. This should say potassium nitrate. The sulfate here is wrong. I will correct that and repost it. But this sulfate should say nitrate. So now what I want to do is I don't have a scale that's going to measure out the right number of moles of something. I do have scales that will measure the right number of grams of something. So if I have the molar mass of potassium nitrate, which is 101.1 grams per mole, then I can determine how many grams of this stuff I need. So I would need 0.379 grams. And the way that I would make this, the actual answer to this question is I would dissolve 0.379 grams of potassium nitrate in enough water to make 250 milliliters of solution. We do not simply add 0.379 grams of potassium nitrate to 250 mils of solution. The reason we don't do that is because this stuff takes up space too. So the volume would no longer be accurate, or precise, I should say. So we add it to enough water to make that much solution. So usually we'd add it to like 100 mils of water, dissolve it, and then just keep adding water till we got to the right one. Doing this in just one step. Here I've broken out in 3 steps, or 2 steps I should say, so this is just one step. My molarity times my volume times my grams per mole will give me units of grams. Liters cancel with liters, moles cancel with moles, all I'm left with is grams, and so that's my answer for today. And it's a fairly straightforward process. We pause there for a quick second, see if are there any questions. There's only about 6 or 7 of us, and so if you have a question you want to ask, please feel free to unmute yourself and ask. And you can do that at any point during the lecture. That's fine. So any questions on anything that you've seen so far? Okay. So we can change the concentration of the solution once it's been made. And there's a couple ways to do that. The first way is pretty straightforward. You can increase the amount of solute. That is, if I've got like salt water and I want to make it saltier, I add more salt. Right? So increase solute. That's one way to do it. The second way is to increase or decrease the amount of solvent. If I increase the amount of solvent, that is, I have salt water, but I want it to be less salty, I can simply just add more water so that the concentration, that I'm increasing the volume of that, so its concentration goes down. I haven't changed the moles of solute, so if my numerator stays the same, my denominator gets bigger, my ratio between the two gets smaller. I can also decrease the amount of solvent. This is something I don't do all that much, but though you might if you are a certain kind of cook. If you want to make a reduction or something, you end up heating something so that its solvent evaporates away and all the stuff that is not solvent stays. We do that in a device called a rotovac. They're common in organic chemistry. It's nothing we really do a lot in this class, but it's something that exists. And the process of us increasing solvent to decrease concentration is called dilution. And so the process behind dilution is this. If I know a molarity and a volume, let's call it M1 and V1. I multiply those two things together, liters cancels, I'm left with units of moles. If I have another molarity and volume and I multiply them together, I'm also going to get moles. Now, if it just so happens that this number of moles and this number of moles are equal, then I can write this little equation, M1V1 equals M2V2. So if I want to make a dilute solution from a concentrated solution, some of you might have concentrated fruit juices that you add water to just the right concentration. All that we're doing there is we are going to take a certain number of moles out of the stock solution, put it into a final solution, and change its volume. So I take, if M1 is the molarity of my stock solution, V1 is the amount of it I took. M2 is the new molarity, once I bring it to a new volume, V2. So it's a relatively straightforward thing to do, but it's based on this idea that all the moles that came out of this are the moles that are in my final. So how would you prepare a 500 milliliters of a 3 molar nitric acid solution from a stock solution of 15.8 molar nitric acid? 15.8 is the most concentrated nitric acid you can actually get. And you got to be careful with that. That is nasty stuff. So I have this really concentrated solution. I don't need it to be quite so concentrated. So what I'm going to do is dilute it. Right? It takes some of this and then add a certain amount of water to get to a concentration that is just 3 molar. So the solution is really asking the question, what volume of stock do I need to make 500 mils of a 3 molar solution? Okay, so let's start setting this up. M1V1 equals M2V2. That's an equation that's going to be quite useful for me now because all the moles I take out of my stock solution are going to be in my final solution. So I don't know how many milliliters or what volume I should take out of this solution, 15.8 molar. That's my variable as I'm trying to find out. to make a solution that is 3 molar with a final volume of 500 mL. Well, this is the only variable I have, so I can just solve for it. So 3 times 500 divided by 15.8, and that will get me 0.949. So I need a little less than 1 milliliter in order to get, and dilute it to a final volume of 500 milliliters in order to get to a final concentration of 3 molar. So the one thing I want to point out here is you notice that I've got moles per liter times the volume, moles per liter times the volume, and my volume here is milliliters. This volume is liters. I never changed the unit. Ultimately, that's okay, because if this unit is also in milliliters, that unit milliliters cancels from both sides. So as long as I'm consistent using milliliters for both of these, then I'm okay. If this one is in liters and this one is in milliliters, that is inconsistent. That is not okay. So long as I have these in the same unit, I do not need to change the units of liters if I don't want. Before I move on from that, are there any questions on this dilution? There will be sort of like a challenge question. It's one of the ones that I had put out. So the 3 questions that I previously published to you guys, one of them deals with dilution. Okay, so let's go through and see. Lots of different types of solutions exist. This is a very common one, the electrolytic kind. So most solutions that we deal with are made with water. It's a solvent, we've got a lot of them. So you make a lot of solutions with it. A solution that contains sodium chloride would be shown as sodium chloride with a little AQ after it stands for aqueous. That's what this AQ means here, aqueous. And when sodium chloride is aqueous and goes into water, it doesn't exist as sodium chloride anymore. It exists as separated sodium and chloride ions. This is a nice picture of that. I've got this nice array of sodium and chloride ions. And when water gets in there, water can sort of wedge between these sodium chloride ions and separate them, and keep them separated. So the negative chlorides go off and these positive sodiums go off and they're separate. So they're no longer together. So I've got a collection of sodium ions and chloride ions. So a species that breaks up into ions when it goes into solution and completely breaks up into ions is what's known as an electrolyte. This word right here has meaning. So when you see something that says contains electrolytes, and that is something that is Gatorade's claim to fame, or what Brano gives points, it's a thing that's there, and the reason it's there is because whatever solids were put into there, they completely break up into ions. You can calculate the concentrations of just those ions. So what's the concentration for each of the following solutions? So for all the ions in these. So I've got a 0.15 molar solution of sodium sulfate. I've also got a 0.25 molar solution of potassium phosphate. Now, I'm going to figure out the concentration of the ions in just this one solution, 0.15 molar. So let's go and figure out what that is. First of all, I probably need the formula for it. So sodium sulfate is Na2SO4. And if I've got a 0.15 molar solution, that's moles of sodium sulfate. Every mole of sodium sulfate contains 2 moles of just sodium. And so 2 times 0.15 is 0.3. So I've got a 0.3 molar solution of sodium sulfate. So it's just 2 times that. And the reason for that is because I've got 2 moles of sodium for every 1 mole of sodium sulfate. To do the same thing for sulfate, I've got a 0.15 molar solution of sodium sulfate. Every mole of sodium sulfate contains 1 mole of sulfate. Sulfate is the anion, not sulfur and peroxide. The group, SO4 2 minus. So 1 mole of sulfate is in 1 mole of this. So my concentration would be that of the solution. For every 1 mole of this, I have 1 mole of this. So my solution is 0.15. Questions on this before I move on to the part B example of this? Okay. So now I've got a 0.25 molar solution of potassium phosphate, and it's laid out in the very same way, so I'm not going to really do it line by line. Basically, I need to know the formula, K3PO4. And I've got a 0.25 molar solution. And for every mole of potassium phosphate I have, I've got 3 moles of potassium. So 0.25 times 3 is 0.75. For every mole of potassium phosphate I have 1 mole of phosphate. So it's 0.25. Guys, any questions on those? Should make sense that if when this breaks up, it breaks up into 3 potassiums and 1 phosphate. So I should have 3 times the potassium and just a normal amount of phosphate. Okay. So there's the other, and I shouldn't say just the other because it's not necessarily a binary thing. There are different groups of these things. So one extreme is an electrolytic solution. So that is one that contains ions when it goes into solution. And the other is something that dissolves into solution but does not contain ions. So some species, if they go into water, they actually do dissolve, they mix, they form a solution, but they're not electrolytes, which means they don't give up any ions. Sugar is a great example of that. It dissolves in water much better than salt does. So when solid this goes into water, it becomes aqueous this, and I still have water on the other side. I don't know why I didn't want to put that in there, maybe to avoid confusion, but the idea is that water is still there, and this, when it goes into solution, does this. Now, we've got this neat little battery thing here, so let me explain this. We've got the 2 leads of a battery, one going to one piece of metal in the salt solution, the other one going to this other piece of metal here, and they're connected to this light bulb. So if these 2 pieces of metal were touching each other, we'd have a closed circuit and the light bulb would light. They're not touching each other, but they're in a solution that contains salt water, and this solution is able to conduct electricity. That's where it gets its name electrolyte. So the ions in the solution are capable of conducting electricity. This solution here, we dump this into water, it dissolves, but creates no ions. Because there are no ions, and these 2 things are not in contact, we do not get this to light up at all. So it's kind of a cool demonstration. And if I was to do this with tap water, just if I were to go to any drinking fountain that is currently giving out water, it would light up. Because our drinking water contains some ions. One of them is fluorine, and fluoride, I should say. And the reason for that, we're doing this for our dental health, but there are some other things in there that help disinfect the water. So we're never drinking water. There are always some ions. So here's the challenge problem. And this is very much like what you might do in a lab. We made some solution by dissolving a little bit of silver sulfate and enough water to make 250 mils of solution. 10 mils of that solution was diluted to a final volume of 75. And it was found that the concentration of silver ions in that solution was 0.00250 molar. So what mass silver sulfate was dissolved? Hopefully you tried something like this. If not, it's okay. It's a complicated problem. Well worth trying. So here is a slightly worse view of it, but the best I can do for taking pictures and putting up your handwriting. Now, a solution was made by dissolving all that silver sulfate, and so I needed to underline the silver sulfite, and I underlined it silver ions to show that I'm getting the concentration of silver ions, not silver sulfate. So M1 V1 equals M2 V2 seems like a good place to start, so I'm kind of starting here and working backwards. So my 75 milliliter solution contained this concentration of silver ions. And it was made by taking 10 mils of some other solution. So 10 mils, and here's my M1. I don't know M1, that's what I'm trying to find out. So this is the concentration of the solution that was made by dissolving some mass of silver sulfate into it. So if I go through and solve for that, I get 0.01875 molar silver ion. So that's what I know right now. I know the concentration of silver ions, not the concentration of silver sulfate. I also know it in the stock solution. Now, this is the concentration of silver in my stock solution. My stock solution had a volume of 250 milliliters, which I converted to liters here. Now, this I do have to do because That's how I get to units of moles of silver. So now I've got liters that'll cancel with liters, and every mole of silver sulfate contains 2 moles of silver. I've got a 1-to-2 ratio. And every 1 mole of silver sulfate weighs 311.799 grams, which has a final mass of 2.92 grams. So 2.92 grams of silver sulfate was dissolved in enough water to make 250 mils of solution. Okay, I'm sorry, this number here, 250 mils of solution. 10 mils of that solution was diluted to a final volume of 75 mils, and that resulted in a solution that had a 0.00250 molar concentration of silver. Okay. As long as you can keep track of your units, this isn't that hard. But it's the keeping track of your units and trying to get out what you're asked. That's the tricky part. But this practice makes perfect. Before I move on to the stoichiometry, are there any questions on this?
Can you just real quick re-explain that M110 equals the molarity?
Yeah. Might be most helpful for me to do it from here. So looking at my problem, I want to start with the thing that's going to give me units of moles the fastest, and that is this molarity and this volume. So I have a 75 milliliter volume of solution.
Okay, I see it now.
Yeah, and it has this concentration.
Thank you.
By taking 10 mils of some other solution. Okay, so that's how I plug this in.
Okay.
And then that gives me that number. Does that help?
Yeah, I understand it now.
Good.
Thank you.
You're welcome. Anybody else? Okay. So let me move on to the thing you've been waiting for today. I know you woke up really excited about it. Solution stoichiometry. Okay. Awesome. Well, it should be no surprise that we can use this in figuring out what goes into and comes out of chemical reactions in terms of mass. So one thing to keep in mind is we now have 2 ways to determine the number of moles in a reaction. One's mass. We just convert that to moles by dividing by the molar mass. That's nothing new. The other is molarity and volume. If I have moles per liter and liters, that will also give me moles. So I have more than one way to get at moles per something. We're going to use this to our advantage in these solution stoichiometry problems. So, what volume of potassium phosphate is needed to react completely with 95.4 mils of a 0.102 molar solution of copper chloride? And then the second question, what mass of copper phosphate is made? Sorry. So here we are, we're looking at this equation here. I've got sodium phosphate, copper 2 chloride making copper 2 phosphate, and sodium chloride. If there are no coefficients here, it's a good indication that you should probably check to see if it's balanced. This is not balanced. So if you go through and balance it, 2 sodium phosphates and 3 copper chlorides goes to make copper 2 phosphate and 6 sodium chlorides. Now, I need to start with something that's going to give me moles. Here I've got a molarity but no volume. Here I've got a volume and a molarity. So that's the place I'm going to start. These 2 pieces of information here. So I've got a 0.102 molar solution of copper 2 chloride, and I've got that much of it, 0.0954 liters, or 95.4 mils. Okay. Units of liters canceled, so now I have units of moles of copper chloride. 3 moles of copper chloride react with 2 moles of sodium phosphate. Yes, this is my mole to mole ratio, just like we had it when we did stoichiometry before. But the question is asking me what volume of this stuff is needed. So I want to get rid of units of moles and get units of volume. The way that I do that is I say that I use the solution, and every 1 liter of solution contains 0.175 moles of sodium phosphate. Okay. So liters will cancel with liters. Moles will cancel with moles. These moles will cancel with these moles. I'm left with units of liters. The question's asking me about volume. And so that comes out to 37.1 milliliters or 0.371 liters. Either answer is correct. They're identical. So that's how we can use solutions in stoichiometry to figure out what's going on. Now, it shouldn't surprise you that we can do the same thing with a mass. So again, I'm going to start with the thing that gives me moles. I could have started with the answer I got here and this number, but it's always safer to use what's in the problem. Should I have made a mistake here, I'd be carrying that mistake forward. So there's my molarity, there's the volume. 3 moles of copper 2 fluoride goes to make 1 mole of copper 2 phosphate. Every mole of copper 2 phosphate weighs 380.5 grams. So liters cancel with liters, moles with moles, moles with moles, and with units of grams. That's exactly what we wanted. That comes out to 1.23 grams of copper 2 phosphate. Any questions on that solution? It works just like stoichiometry that you've seen before. No real changes, no real surprises. As a result, we can do other things that you can do with stoichiometry. Here's an example. I've got a 25 ml sample of 1.2 molar potassium chloride, and I mixed it with 15 mils of 0.9 molar lead 2 nitrate. The solid we make from that, lead 2 chloride, is collected and dried, and it's found to have a mass of 2.45 grams. Determine the theoretical and percent yield of the reaction. Goodness, there's a lot of information. Now, a couple things. One, this isn't balanced. That'll need to be fixed. I have enough information to get moles of KCl. I got volume and molarity. I have enough information to get moles of lead nitrate. I've got volume and molarity. I even have information about the mass of this, but this is like an actual yield. I made 2.45 grams. So I don't think I can use that for this. So since I know moles of both my reactants, that means that this is a limiting reagent problem. Okay, so there's a blurrier version of the same thing, and I underlined the pieces of information that are important. I balanced the equation, 2 potassium chlorides and 2 potassium nitrates. Everything else is balanced. So I'm going to start with this bit here. I have a 1.2 molar solution of KCl and 25 milliliters of it, 0.025 liters. 1 mole of lead chloride comes from 2 moles of KCl, and 1 mole of lead chloride weighs 278.1 grams. So when I run this through my calculator, I would get a mass of lead 2 chloride. That's assuming that I use all of my potassium chloride. What if this is my limit? Well, let's see. So I have a 0.9 molar solution and 15 milliliters of it. 1 mole of lead nitrate forms 1 mole of lead 2 chloride. And a mole of lead 2 chloride weighs 278.1, just like I did up here. So really, this is the only part of the equation that's used. When I figure out my answers, I would make 4.17 grams if the top one ran out, and I make 3.75 grams if the bottom one. This is the smaller of the two numbers. It makes it my limiting reagent. So what that means is that 3.75 grams is the most lead chloride I can expect. That is my theoretical yield. So that's the answer that I'm looking for. Next, I can figure out my percent yield because I was told that in this reaction, 2.45 grams is what ends up actually coming out of that. So I got 2.45 grams. I should have got 3.75. Multiplying that ratio by 100 gets me 65.3%. Not a bad yield, not a good one. There's still a bunch of lead in there, but not bad. Okay. So this is the reaction that we're going through, and it's really quite straightforward. It works just like you did with regular stoichiometry. So you can expect to see questions like this in your homework quiz as well. You guys will get an email sometime tomorrow telling you what you can expect in the quiz. That's it. Relatively painless today. That doesn't mean Thursday is going to be painful. So,
Thank you.
welcome. Questions, concerns, comments, violent objections? All right. If you guys don't have any questions, we're done. And I'll be posting this to the class website not too long from now. So usually it takes about half an hour or so to get the video compressed up to YouTube. And
All right.
do well, and I'll see you guys on Thursday.
Thank you, sir.
You're welcome. Bye now.